Hey there, it's Shannon Magic Myers, and today we'll be checking out solution curves without a solution. So, in this section, we check out how a DE can provide information about how its solutions behave. This is used for a first order differential equation for which we cannot find a solution or invent a method for solving it analytically. Two ways to qualitatively analyze solutions of differential equations are direction fields and autonomous solutions. All right, direction fields allow us to examine how a solution behaves near a certain point and its end behavior as x approaches infinity. So, let's take a look at slope. Recall that differentiability implies continuity. That's from Calc 1, in case you forgot. So if a differential equation is differentiable on its interval I of definition, it follows that it must also be continuous on I. The function f in the normal form dy dx equals f of x and y is called the slope function or the rate function. The slope of the tangent line at some xy at x on a solution curve is the value of the first derivative dy dx. Suppose that x and y, this order pair x, y, represents any point in a region of the xy plane over which f is defined. Now, the value f at x and y that the function f assigns to the point represents the slope of a line or line segment called a lineal element. Whoops, sorry. All right, so let's see what we have going on here. A lot of words, not enough pictures, right? So let's check it out. If you have something like this, and we've got x here, we have y here, and I don't know, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now, suppose we are looking at the slope at a certain point, right? So these little lineal elements, basically, let's say we were looking at the order pair 2, 3, something like that. So right here would be the ordered pair 2, 3. Now let's suppose our slope was given as 1 say the slope was equal to 1 unit. Now, as we know, 1 over 1 and negative 1 over negative 1 would give us little slope triangles, and so we could make a lineal element that has a slope of 1 right at that order pair. So this one is called a lineal element at a point. Okay, so let's say we've got, a similar situation, but we're looking for tangency. So again, we are interested in this point at 3, 2, and we're looking though at how the graph is behaving, right? So you've got, suppose this is our function, goes through that point. It's looking like this, and now this here, this lineal element is now tangent to the solution curve. So our lineal element is tangent to the solution curve at let's say this, that passes through the point. So just a little bit of a different perspective. So this again is 2, 3, and we're just taking a look at how we could use, you'd have like tons of these little line segments, and what would happen is you'd be using them, they'll look kind of like a wave, and you'll know which way you would draw the solution curve, right? Depending on which family you want to follow, which part of the family you want to follow. Cool? All right. So, direction field. If we evaluate F over a rectangular grid of points in the XY plane and draw a lineal element at each point X and Y of the grid with the slope at F of X and Y, then the collection of all these line elements is called a direction field. Also, we often call this a slope field of the differential equation dy dx equals f at x and y. This field visually suggests the appearance or shape of a family of solution curves of the differential equation. So, a single solution curve that passes through a direction field must also follow the flow of the pattern of the field. It is tangent to a linear element when it intersects a point in the grid. For the differential equation, again, dy dx equal to f at x and y, any member of the family of curves, f at x and y equal to c, where c is a constant, is called an isocline. These are so cool. Linear elements drawn through points on a specific isocline all have the same slope. So here we go. For this first example, we want to do this by hand at first. So we're going to sketch isoclines, f of x of y equals c, for these different slope, these different values for c. So dy dx is equal to x squared plus y squared. C is a quarter, c is 1, c is 9 quarters, c is 4. We're going to construct a direction field over a grid by drawing linear elements with the appropriate slope at chosen points on each isocline. In each case, we use this rough direction field to sketch an approximate solution curve for the initial value problem consisting of the dE and the initial condition that y at 0 is 1. All right, let's do this. So, here we go. Let's go ahead and take a look at, we're going to plug in values for c, correct? And then we're going to find f of x of y equal to c. And remember that f of x of y was given to be x squared plus y squared, because it is on the other side of that equation, right? That's the format. And then we've got these different values of c. We've got a quarter, 1, 9 quarters, and 4. And x squared plus y squared equal to c squared is a circle, right? So let's do that. Let's figure out what we would square. So if we put this equal to 1/2 squared, isn't that the same as a quarter? Cool. And then we'll draw it in a moment. We'd have x squared plus y squared is 1 squared for this next one. Plugging in 9 quarters, we would have 3/2 squared. When you square 3/2, you get 9 quarters. And then we'd have x squared plus y squared is 2 squared, because that would give us c of 4. Groovy? Now, if I come over here and then I draw this little grid here so that I can make my circles, and here we go. And then I'll draw the circles in different colors. So for the very first one, we've got a circle. All of these have a center at the origin, 0, 0. And then the first one has a radius of 1/2. So my circle will look something like this. All right, hopefully that's close enough. I think so. So that's my first circle, and that was for C is a quarter, and then next circle, let's do a blue one. So we'll do for C is 1. That one was better, huh? And then next up, when we go to C is 9/4, so we're going to 3 halves, 1 1/2, the quantity squared. So something like that. And then finally go into when C is 4. So that was when we had a circle with radius of 2. Apparently my scale is not super great right there. But you get the thought here. All right, so we've got these circles drawn really rough. Now, here we go. Let's now take a look at slope. So if we come over here and we find out the slope at these different values. So remember that if you take a look at f of x and y was x squared plus y squared, and now instead of doing these c values, we're looking at what the actual slope is. So we have f of x and y, and then we have the actual slope as an output. So actually I'll do it like this. So we'll have x, y, and then the output at f of x and y. And here's this super awesome, amazing thing. You find one point on one of these circles, and our little slope lineal elements are going to be the same for that whole circle, every point on that circle, and that's why this is so amazing. So one point on the circle, the smallest one was 1/2, 0, and so f of x and y is just going to be 1/2 squared plus 0 squared, which is 1/4, right? So it's for every 1 up, it goes over 4. So it's going to be not very steep, right? So here, the hardest thing, honestly, is to make it. So that was where at 1/2, 0. So here we go. It's not going to be tangent to the little circle, so we're not thinking that. It's a slope of 1/4. So here we go. So this one is going to be really somewhat like this. Not very steep. But the really awesome thing is through every single point on the circle, this little pink circle, every point, it's got the same lineal elements, right? So it really helps us to make a field. All right, let's find out another one. So again, I'll do it on x is 1, y is 0. We'd get 1 squared plus 0 squared equals 1. So we'll have a slope of 1 on the blue circle. So the blue circle, a slope of 1 would be roughly like this. And then I'll just make a bunch of these lineal elements on my circle. Cool, cool. All right, now next up we can do 3/2 0. So again, we'll get 3/2. We're squaring it, plus 0 squared equals 9/4. And 9/4 is just it's getting more steep. It's a little bit more than 2, right, for our slope. So the orange triangle, for every, it's going to be a lot more steep, right? And so it'll be probably about like this. It's too much like the other one, right? And then you'll start seeing kind of a wave of how the solutions can go. And so we'll do one last one here wherein x is 2, so we'll have 2 squared plus 0 squared is 4. So a slope of 4, super steep, especially when you're just doing these little lineal elements. Usually a little more careful with how I the slope, but you'll get the idea. Awesome, awesome. So then when I take a look at these fields, right, if we want to draw in our graph, get something that'll show up. It a little thicker. All right, so here we had an initial condition of y at 0 is 1. So when we want it to go through the ordered pair 0, 1, right? So we're going to look right here, and our graph following that might be a little too big, following these, the path of the slope, the little slope deals, it'll do something like this, okay? It'll look something like that. Cool, cool? All right, so that's how you could, I don't really like how I did the little tail thing, so it looks something like that. So that's how you can use a direction field or slope field to estimate a solution curve. And another really cool thing about this is you can, that those isoclines basically allow you to make a bunch of these little lineal elements super quickly when you have that relationship going on. Cool, cool? All right, so now we'll go back and let's use some technology to generate the slope field. So somebody made this slope field. Hopefully I can select it. Maybe not. Okay, I think I still have it up here. But it's somebody who was did GeoGebra slope field. Here we go. And so here, let's go ahead and take a look at ours. And ours was what? X squared plus y squared, right? So we're going to have x squared plus y squared. Enter. And take a look. Now this is really cool, this generator here. It should work, the link should work on your handouts. But this generator is really cool because you can take it to the point where you want it for the solution. And we wanted this to be at 0, 1. It's being kind of grumpy here. doesn't let me just plug it in. Closer. Pretty close. One little note here. When lineal element is positive, so it has, in other words, a positive slope, what do you think's happening? The solution is awesome, increasing. Remember that from Calc 1. And when a lineal element is negative, the solution is decreasing. So all of our lineal elements on our graph were going to be positive because both of the x and y are squared. So as you can see, all of these solutions are increasing. Cool, cool. All right, so now let's look at autonomous first order differential equations. So an ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. If the symbol x denotes the independent variable, then an autonomous first order differential equation can be written as f at y and y prime is equal to 0, or in normal form as dy dx equals f of y, because you just have functions of y, there's no x in there. So if you look back to the applications that we covered in 1.3, the independent variable was time t, and this variable did not show up explicitly in the equations. Therefore, the equations are time independent. And thus autonomous. So if you want to go back and check those out, it might be worth it. Okay, critical points. The zeros of the function f in dy dx equal to f of y denoted by c are called critical points. A real number c is a critical point of the autonomous differential equation, which again is dy dx equal to some function of y, if it is a 0 of f, or equivalently if f evaluated at c equals 0. A critical point is also called an equilibrium point. Or stationary point. If f is a critical point of dy dx equal to f of y, then y at x equal to c is a constant solution of the autonomous differential equation. A constant solution, y at x equal to c, of our differential equation dy dx in some function of y is called an equilibrium solution. So equilibria, that's the plural, are the only constant solutions of dx equal to f of y. We can see when a non-constant solution, which would be in the form y equals y at x of this same guy, dy dx, equal to f of y, is increasing or decreasing by determining the sign of the derivative, dy dx. Don't worry, we'll have an example of all this stuff coming right up. Okay, solution curves. Since the function f in dy dx equal to f of y is independent of the variable x, we may consider f defined for minus infinity less than x less than infinity, or for 0 less than or equal to x less than infinity. Since f and its derivative f prime are continuous functions of y on some interval I of the y-axis, the fundamental results from that theorem in chapter 1, 1.2.1 hold in some horizontal strip or region R in the xy plane corresponding to I, and so through any point x0, y0 in R, there passes only one solution curve of dy dx equal to f of y. So the solution curve is unique. Here are some conclusions we can draw about a non-constant solution. Y of x of dy dx equal to f of y. If x0, y0 is in a subregion R sub I for I equal to 1, 2, and 3, and y at x is a solution whose graph passes through this point, then y at x remains in the subregion Ri for all x. By continuity of f, we must either have f of y is greater than 0 or f of y is less than 0 for all x in some subregion R sub I, where I is 1, 2, and 3. Since dy dx equal to f at y at x is either positive or negative. They haven't barked all day, and now that I'm making a movie, my dogs are barking. In a subregion Ri of course, I equal to 1, 2, and 3. A solution, y at x, is strictly monotonic. So remember what that means? Good. Y at x is either, it's really non-increasing or non-decreasing, but our author says increasing or decreasing. In the subregion Ri. Therefore, y at x basically can't oscillate, so it can't be oscillatory, which means it bounces back and forth between values, nor can it have a relative extremum. All right, almost to our example. If y at x is bounded above by a critical point, C1, then the graph of y at x must approach the graph of the equilibrium solution, which remember is a constant, y at x equal to C1, either as x approaches infinity or as x approaches negative infinity. If y at x is bounded, that is, bounded above and below by 2 consecutive critical points, then the graph of y at x must approach the graphs of the equilibrium solutions y at x equal to C1 and y at x equal to C2, one as x approaches infinity, and then of course the other would be as x approaches negative infinity. And then finally, the last case, if y at x is bounded below by a critical point, then the graph of y at x must approach the graph of the equilibrium solution, y at x equal to some C3, either as x approaches infinity or as x approaches negative infinity. Cool, cool? Okay, so let's take a look here at just some different things that we'll find out, because it's weird. We're working with slopes, right? So now we're going to look at attractors and repellers. Okay, so here we go. Now, you can have a situation where a critical point is attracting. So if you've got these critical points, we'll just call them C. If it is an attractor, if C is an attractor, so our y at 0, say it's right here, it's being attracted, pushed towards C. So we can say that limit as x approaches infinity of y at x equal to C asymptotically, can't talk anymore, is asymptotically stable because it's being pushed towards C. So that's also known, aka also known as an attractor. So this is the case, this is one of the first cases. Now let's say that you had a situation where you had y at 0 somewhere, and then your arrows, right, were moving, both of them were being repelled, C was repelling them away. And so in this case, what happens is, as x approaches infinity, all solutions of y at x move away from C. And you'll see this in a minute. It's really cool. And so this is considered to be, C is unstable, which is also known as a repeller. And so this one, I probably should have said C is asymptotically stable. All right. Now, if we look over here with these guys, sorry, I'm going to drag them over. Suppose you have something like this, where you've got y0 here or here, right? So you could have a situation where the arrows are going the same way. So on one side you're being repelled and on one side you're being attracted. So in this case, C is considered semi-stable if on one side, C is attracting and on the other side C is repelling. Solutions. Cool, cool? So let's put it all out in here. Suppose that y at x is a non-constant solution of the autonomous differential equation dy dx equal to f of y, and that C is a critical point of the differential equation. There are three types of behavior that y at x can exhibit near C. And that is, it can be an attractor, it can be a repeller, and it can be semi-stable. Groovy? All right, so here we go. Let's finally look at an example. So please find the critical points and phase portrait of the autonomous differential equation dy dx equals quantity y e to the y minus 9y all over e to the y. We want to classify each critical point as stable, unstable, or semi-stable, and then by hand we'll sketch typical solution curves in the regions in the xy plane determined by the graphs of the equilibrium solutions. Okay, so let's do this thing. We have f of y, right? And f of y is right in here. It's equal to y e to the y minus 9y all over e to the y. Groovy? Now we want to find the zeros of this. So to find the zeros of this, you set it equal to 0. e to the y is never 0. And when we multiply e to the y times 0 to clear the fraction, it just zeroes out. So we still get 0 equals y. I'm going to factor out the y. We'll be left with e to the y minus 9. So y could either be 0 or e to the y minus 9 could be 0 using the zero product property. And this in turn would give us that e to the y is 9. A logarithm is this is our exponential, right? So if we natural log both sides, or evaluate the natural log of both sides, we will have y equals natural log at 9. And just so you know, natural log at 9 is approximately 2.20. So here we go. We've got these two different solutions. So let's make our phase portrait. So the phase portrait they're talking about consists of an interval, we need the sign of f of y, we need f of y, we need to describe if it's increasing or decreasing, and then we need to know which way the arrow points. So how many intervals did we make from this? Good, you've got 2 critical points. We're going to make 2 intervals. So you could have an interval from minus infinity to 0, because one of our critical numbers was 0. It could go from 0 to natural log at 9, or it could go from natural log at 9 to infinity. Cool, cool? And then continuing, the sign of y, f of y, well, we have to figure that out using a value in the interval that is not the critical number. Because if we use the critical number, we'll just get 0, right? So the sign of f of y is going to be, let's see, so you can grab a calculator, you can kind of see what happens when you graph. I actually graphed this in terms of, x, so it's going to look not quite right. But it turns out that if you look at these values here, first of all, between 0 and natural log at 9, you've got, it's going to be negative, and then the other intervals will be positive. This is what we have. So the sign of f at y is, we said it was positive on the tails there and negative on that one little piece. And f of y, therefore, it's, remember, slope. So it's going to be increasing where it's positive, and it's going to be decreasing where it's negative. Sorry. And then the arrow, does it point up? Does it point down? Well, that's where you kind of look at that graph. So if you kind of make this picture, right, and you think that of this point being our C2 is natural log at 9. You've got another point, C1, which was 0. Well, and we have this guy here would be an attractor. So let's take a look at making the little graph. So we know we have these solutions. So as we are looking at our different solutions, if this is 1 and 2, and then of course 0 would be down here. So you basically have y at x equal to 0, so that's one of the lines. And then we have this guy here, where y at x was equal to natural log at 9. Now, what do we know? Well, the sign of the f at y, which is the output of the derivative, is positive at the tail, so it's increasing, and it is negative in the middle horizontal region. So, you've got these 3 different regions made up. So call this one region 1, right? Well, region 1, it's being repelled away, right? So it could look something like that. And then, actually this would probably be region 3, yeah. And then if we called this one region 2, well, it's decreasing in region 2, so it could look something like that. And then in region 1, it actually would be, it could look something like this. It's being attracted, remember, to that point. Pretty cool, right? All right, so now looking at a translation property, okay, and we'll be finishing up here soon. It turns out that solution curves of an autonomous first-order differential equation are related by the concept of translation. If y at x is a solution of an autonomous differential equation, remember dy dx equals f at y, then y1 at x equal to y at x minus k, where k is a constant, is also a solution. This is due to the fact that lineal elements passing through points on any horizontal line are parallel. So let's go back to that one little site that was so helpful. Now this one isn't autonomous because it has an x and a y, right? But if we just took a look at something like, I don't know, y prime equals y, then you can see how all of the, it's really cool how all of the little elements on a horizontal line, so if you move this over like super carefully horizontally, all of them are the same, which is pretty amazing, right? I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please hit that like button and subscribe. Bye.